All right. Hello, everyone. So I'm going to summarize what we have covered in class, which topics we have covered. So in the previous week, we have talked about these two types of vectors that actually transform under inversion. So one kind was the polar vector, which actually transforms in the same way that we expect. So under inversion, they are going to change sign. So the position vector, for example, so position, and the momentum vector, which is essentially mass times the time derivative of the position. Sorry about that. So that's the momentum vector. These are polar vectors. So they are going to change sign, change direction basically under inversion. But the angular momentum, so that's R cross B, that's not going to change sign. So these are, that kind of vectors are called pseudo vectors, right? In any case, I mean, so we naturally use both polar vectors and pseudo vectors in physics in lots of different places. But since we don't do this inversion transformation all the time, you may not have noticed that some of these are like these special kinds of vectors. So why we need to talk about them in here? Because if your interactions, your physical system has inversion symmetry, then polar vectors and pseudo vectors somehow appear in some certain places, but they don't appear in other places, right? So for example, the cross product of two polar vectors is a pseudo vector. That's something that we have, I think, mentioned last week, right? That's one of the things, for example, I don't know, I mean, magnetic field, for example, is a pseudo vector, and the electric field is a polar vector, and you can actually see the signs of all of these natures of these vectors in different places. Okay, it's just, I think I'm going to remind you this. So, yeah, whatever. All right. So I'm going to talk about the angular momentum in a moment. So it turns out that, well, there are these core forces in nature. So the gravitational force, there's this electromagnetic force and the strong force, three of them, and then there's this the fourth one, the weak force, right? So we don't actually see in classes the strong and the weak force, but I mean, particle physicists actually see them. So it turns out that these three forces have inversion symmetry. I mean, so the interactions of particles with these forces somehow display inversion symmetry. And so as a result, I mean, we can actually discuss various, I don't know, various things with, using that symmetry. So it turns out that the weak interactions violates, so that's violates inversion symmetry. And this is one of the things that I would like to talk about. And then first, I'm going to talk about this. And I'm going to kind of display how the weak interactions actually do this. So this is actually Li and Yang are the first ones to actually propose this theoretically. So they got the Nobel Prize. And Wu has done this experiment, and I'll try to explain how this experiment is done. Right? So that's the first part. And then in the second part, I'll talk about parity, which is closely related to the inversion symmetry. And then I'll talk about the conservation of parity and things like that. Okay. So as a result, I mean, this is going to be about inversion. And today, in the last, I don't know, 10, 20 minutes, I have actually made an introduction to the representation theory. Okay. So let's remember this again. This is the picture of, for example, the hydrogen atom. There's an electron in here. So I think I'm going to try to draw some kind of a 3D picture like that. Yeah, let me try to do it like this, right? So let me exaggerate and draw a bigger hydrogen atom in here. And so that's the bigger nucleus. So it's just an exaggeration. And I'm talking about an orbit like that, right? Okay, so for example, at this moment, the position of the electron is this, and the momentum is like that, right? Momentum is, let's say, pointing into the screen here. So under inversion, the position is going to change to minus r, right? And the momentum also is going to change to minus p. So both of them are going to change sign. But if you just compute the angular momentum, so I think I'm going to use a green coloring here. So the angular momentum in that case is going to be like that. So that's r cross p. It's the same thing as minus r cross minus p. Okay. So if you think at this classical electron on a circular orbit, for example, if you do an inversion, this inversion transformation is going to place the electron on the opposite side of the orbit, but it will still have the same angular momentum, right? So as a result, from that point of view, you can really understand that the angular momentum actually doesn't change under inversion. It remains the same. This is also consistent with the commutation relations. So LI, LJ is equal, sorry, I'm going to write X, Y, and Z in here, so it doesn't matter to write this thing down in the most general possible way. So this is the computational relation of the angular momentum. So it turns out that, I mean, if you think that, well, the angular momentum changes sign, we have an inconsistency in here. So as a result, it is necessary that the angular momentum does not change sign. So this somehow confirms this behavior of the angular momentum. If you remember, for the position and momentum angular commutation relationship, we also do not have any problem because x changes sign and momentum changes sign, and this is okay. But here we have angular momentum appearing in 3 places. So if you just change the sign of all of them, the equation will become invalid, right? So that's somehow confirms that this angular momentum is assoyed away. Okay. So I can actually ask the same thing for the spin angular momentum. So the question is the spin angular momentum a pseudo-vector? All right. And the answer is yes, right? Otherwise, let me say it like this, because the spin operator should satisfy the angular momentum commutation relationships. And so therefore, by using this relationship alone, we can claim that it has to be a pseudo-vector, right? So here, just keep this in mind, right? So we can claim that the angular momentum is a pseudo-vector because it's the cross product of 2 ordinary vectors. We don't have such a chance for the spin angular momentum, okay? So and because we cannot write down the spin in terms of some more fundamental quantities. However, by using this commutation relationship, we get the idea. Right? So it's not possible that the spin can be treated as an ordinary vector, as a polar vector. It has to be a pseudo-vector. Okay. So the next thing is this. All right. So all the angular momenta, therefore, are pseudo-vectors, right? So that's also consistent with this general picture too. Okay, so the next thing is this. This is the weak interaction, the cobalt. So that's the Wu experiment. Okay. It's basically the neutron emission of cobalt-60. So it's just a radioactive nucleus. It does emit some neutron after the emission. So I still didn't look at. So that's the reaction in here. So cobalt-60 is transformed into, I think, cobalt-59 with the emission of a single neutron, right? So it's actually a weak decay. So a weak interaction is actually responsible for that transformation, right? So the idea of the experiment is to actually use polarized nuclei. And polarized means that every nucleus has a spin. So you just somehow orient all the spin of the nuclei. So let me say nucleus, let's say. So orient all the spins of the nucleus in some certain direction, okay? And in the transition, in the decay, so they are going to emit some neutrons in, I don't know, various directions. So the neutron is going to go along that direction. So that's basically the direction of this momentum. And just look at the distribution of the that angle in here. So let's say it like this. So let's f theta is, I don't know, f theta, d theta is, let's say, probability of neutron leaving with angle, let's say, between theta and theta plus d theta, right? So f theta is some kind of a probability distribution for the decay here. Okay. So in any case, so with the if the nuclear spins are polarized somehow, and this can actually be done by using some properties of this cobalt material actually. So you have to apply some kind of a uniform magnetic field, and the nuclei somehow eventually is going to come oriented along this direction or opposite to the magnetic field. But I don't remember which. Probably it is parallel. So sorry about that. So in any case, so somehow you orient the spins, and then you just measure in which direction the neutrons actually leave. Just measure all of them and then try to plot this probability distribution, basically. Okay. In any case, so the idea in here is this. If you just look at this picture in here, so just take a reaction like that, okay? And look at its inversion symmetric situation, right? So let me, I mean, this is just a process, just a single process. Just look at the inversion symmetric process in here. So that's the, just inverting here. So under inversion, so that's inversion. The spin is going to remain the same, so that's not going to change sign, but the momentum is going to change sign. So therefore, this neutron is actually leading along this direction with a momentum of minus p. Okay, so let me erase this part in here as best as I can. All right, in which case, I mean, if this neutron left with angle theta, in that case, this is going to leave with an angle of 180 degrees minus theta, right? So the inversion symmetric picture is going to have a different angle theta, right? So the fact that, of course, the spin is a pseudo vector and the momentum is a polar vector is important in reaching to that conclusion. Just keep this in mind. In any case, if the weak interactions had inversion symmetry, in that case, the probability of this picture and the probability of this inversion symmetric picture should be equal to each other, right? Because of the symmetry. So let's say it like this: if weak interactions had inversion symmetry, then we should have like the probability of a photon emitted in with an angle of 180 minus theta should be the same as the probability of being emitted in the direction of theta. Okay. So this would imply that f theta is a function of theta should have a symmetric shape like that, right? I'll try to draw this like this, right? So this is 180 degrees, so there's a 90 degrees in here, and this is 0 degrees. It should be symmetric around 90 degrees. So I don't know what the real actual shape is actually. So Wu has measured, right? Measured f theta, so that's the experimental one, and the experimental experimental distribution actually does not have that symmetry. Okay? So I don't know how it changes. I have looked at this paper long ago, but I mean, it doesn't have any symmetry at all. So that's the important point in here. So because of that, because of this, then you say that the weak interactions violate inversion symmetry. There are other manifestations of the violation of the inversion symmetry. So it's people just call this as P violation because they use P parity as a word synonymous with the inversion operation. But in any case, so when people say P symmetry of nature, that's actually talking about this. So somehow the weak interactions does not actually have the inversion symmetry, right? So as I said, there are some alternative ways of expressing this violation. In the neutron decay, for example, decay of the neutron to a proton and an electron and an anti-neutrino. So there's always some certain kinds of neutrinos are actually produced in the interactions and things like that. So there are also these kind of manifestations as well, but I didn't go into these kind of discussions. Okay. So I think this is one of the important experiments in physics, actually, right? It's like done in 1950s or 60s. I don't actually remember the dates. There are actually some kind of Wu's original, not the original article, but Wu somehow expresses what has happened during that time and what she has done and things like that. So I suggest that you also read them as well. I mean, it's actually a nice history. Second thing is this. So we basically think of it like that. Right? So we have, let's say we have an electron in here. So I don't know. So let's say this is an electron in hydrogen atom. So let's suppose that the electron has this wave function. I don't know. I mean, I usually draw the wave functions like that. So that's the, let me say, counterplot of electron's wave function. All right. In any case, so there's some kind of a wave function in here. So this perhaps, I mean, shows the parts of the wave function that is it has a certain value. Perhaps the wave function is maximum in here and minimum in here. I don't know. I mean, it's just a symbolic way of actually expressing this. Okay. In any case, when we actually do this inversion, we physically think that we take the electron and then move it to another location. So as a result, if the electron is precisely in here, under inversion is going to be moved somewhere in here, right? So if the description of the electron is quantum mechanical, just like this one in here, in that case, I have to invert the wave function, right? So I have to take this counterplot and then invert this. Okay. So I'm going to call this as psi prime. So that's the inverted wave function. So the transformation is therefore from psi to psi prime in such a way that this wave function psi of r in here is the wave function. So the psi prime of r is going to be related to the old wave function by this relationship, right? You can actually think of it like that. In any case, we actually think that this transformation is actually done by some kind of a linear operator that I'm going to call this as P. So P in here is, can think of this as the parity operator. Some people actually call it like that, or the inversion operator. Okay. But we have to distinguish with the this with the abstract inversion operation as an element of the group O3. All right. So there's this abstract inversion thing. So that's a geometrical operation. This is a mathematical operation that acts on the wave functions of the hydrogen electron in the hydrogen atom. It's actually a mathematical operator. We call this as actually it's a representation of the inversion element J in O3. Okay. You can think of it like that. So J in here is the abstract inversion, geometrical inversion. This is kind of a concrete operator version of that does the same thing on wave functions. So if we have a different physical system like helium atom, in which case there are like 2 electrons, in that case the operator is going to be different, right? So we have an abstract symmetry operation, and we have lots of representations of it depending on what physical system that we are using. Just keep this in mind, right? In any case, we basically, well, the parity operation is basically like that. So P psi gives you a new wave function whose value at R is equal to the old wave function, the value of the wave function at minus R. Okay. Just like the ordinary P operator, so its square is equal to identity. So if you apply inversion twice, you get the same wave function, obviously, that's obvious. We would like to look at the eigenvalue equation in here. Eigenvalue equation for P. So in that case, we actually look at wave functions that's, I don't know, where P psi is equal to lambda psi. So the idea in here is this: since P squared psi is equal to identity, first of all, mathematically, this implies the second one. So if I apply P twice, then I'm going to get the eigenvalue twice in here. But since P squared is equal to identity, this implies that lambda squared is equal to 1, which implies that the eigenvalue is either +1 or -1. Okay. So this implies that there are actually 2 possible parity states. One is called an even parity state, even parity, where the eigenvalue is +1. This is actually, for example, in 1 dimension, this corresponds to a wave function which is even under this inversion, right? Psi of -x is equal to psi of x. So this is like an even function. Okay. That's for even parity. Then there are these states where let's call this psi prime or psi tilde. Let me call this as phi, for example, so that I use a different notation now. So this is a odd parity state. So that's a parity eigenstate where the eigenvalue is -1. In that case, the corresponding wave function is, so if I plot phi, the corresponding wave function is an odd function. Okay. Odd function. This function satisfies the property that phi minus x is equal to -5x. All right. I mean, let's just keep this in mind. So therefore, we can then talk about these parity eigenstates. Okay. In any case, so what's the relevance of these parity states? Basically, there are a few things that we need to state in here, but I don't want to go into the details in here. So it's something called the inversion symmetry. Inversion symmetry of a physical system. Okay. You can actually express it in different ways, but usually we express it in terms of the Hamiltonian operator. So that's the Hamiltonian. Let's just consider this Hamiltonian operator. So the Hamiltonian operator is the operator that actually gives us describes the time dependence. Describes the time dependence of wave functions. Right, it's actually quite hard to describe the connection in here, but I would like to just summarize. So we say that if a system has inversion symmetry, then this also implies that implies something about the Hamiltonian. So we are going to actually, I'm going to write it down like this, but I'm not going to explain why this is the case. So first of all, under inversion, okay, the Hamiltonian transforms as like that. So the Hamiltonian is transformed into a new Hamiltonian, which is given by, this is essentially a similarity transformation. Sorry about that. Sorry. I'm using this ordinary P, right? So that's P inverse P in here, where I use the symmetric transformation, representation of the symmetric transformation like that, right? This is essentially a similarity transformation. Because of some other properties of P in here, H prime is also a Hermitian because the Hamiltonian has to be Hermitian, and things like that. So let me not justify this, but I can kind of give you some certain other things that actually tell us, kind of justifies this, right? But right now, let's just accept this, right? Under inversion, any kind of a operation actually transforms like that. Okay? So that's the definition, let's say. In that case, sorry, we say that H is inversion symmetric if the under inversion, the Hamiltonian does not change, right? So sorry about this. Let's also write this in verse. So under inversion, H does not change. Okay. We can also justify this by using, for example, the function of the Hamiltonian in describing the time dependence of the wave functions, for example, right? I have done this in class, but at this point, it's not really necessary, right? So as a result, I mean, there are some certain ways that I can define what symmetry means, but it essentially reduces to that, right? So the Hamiltonian somehow under inversion, it also has its own transformation. And so therefore, we say that the Hamiltonian is inversion symmetric if under this transformation, under this inversion transformation, it doesn't change. So H prime is equal to H. Okay. There are different ways, therefore, that you can write this thing down. So H is equal to PH P inverse in here. That's the relationship. But if I multiply both sides of that equation with P, then we can get rid of this. So therefore, it then reduces to that equation. HP is equal to PH. So we say that H commutes with P. Okay. I can write this in this expression in a different way. So mathematically, I can write this in terms of the commutator of these two operators being equal to 0. So that statement is basically the statement that that system is, right? System has inversion symmetry. Okay, I can express the condition of symmetry as the mathematical condition that the Hamiltonian commutes with the inversion operator. Okay, so this is also related with something else. So there's actually something called an Ehrenfest theorem. We basically consider the expectation value of time-dependent expectation value of some kind of an observable. For example, this is like the wave function at time t. I don't know, let's say it like this: a hat phi of t integral, for example, right? So since the wave functions change with time, this thing the expectation values also change with time as well. In any case, Ehrenfest's theorem actually tells us how this time, the expectation value changes with time. So the time derivative of A is basically given by the expectation value of the commutator of the Hamiltonian with the corresponding operator, right? So basically, this is the theorem, but that's something that I don't want to prove. In here, it's actually proved in quantum mechanics. But what's essential in here is that the Hamiltonian also, or the commutator with the Hamiltonian, describes how a certain expectation values change with time. Okay? So the Hamiltonian also describes how quantities change with time as well. So somehow that's involved in here. What's important in here is that if the Hamiltonian commutes with that observable, then basically A is a conserved quantity. Well, that's actually, let's just forget about this ifs in here. This is also equivalent to that statement, right? We say that a certain quantity is a conserved quantity. Well, there's a certain definition, but this is mathematically equivalent to that quantity basically commuting with Hamiltonian. So this is the same thing as basically the expectation value of A is time independent for all possible states, actually. So that statement is equivalent to that mathematical statement. Right? So in any case, so therefore, I can actually relate this to the symmetry, actually. In any case, so that's the last statement in here. System has inversion symmetry. This is equivalent to the statement that the expectation value of this parity operator is conserved. Okay, so therefore the symmetry somehow is related with the conservation law. So that's the essential, the essence of the Noether's theorem. Noether's theorem. Okay, Noether's theorem says that if there is a symmetry, then there is a corresponding conservation law. Noether's theorem have classical and quantum mechanical counterparts. In the classical counterparts, it's necessary that the symmetry has to be a continuous symmetry. It has to be a D symmetry. But in quantum inversion, even discrete symmetries like the inversion obeys this conclusion. So if there's a symmetry, then there's a corresponding conservation law. So if there's this inversion symmetry in a physical system, therefore the parity must be conserved. The average value of the parity must be conserved. Okay. So that's important in here. So I'm just going to give one example of parity in the hydrogen atom, because we have said that the electromagnetic interactions have inversion symmetry. So as a result, if you just consider, I don't know, a transition, for example, in an atom, there is no weak interaction in here. It's just the electromagnetic interactions. And so therefore, in a transition in an atom, the parity must be conserved. Okay. So we are going to state this as an example. Okay, so let's say this is the hydrogen atom, right? So the energy eigenstates. Let's just forget about it. About the spin. There are actually three quantum numbers, MLM, and three coordinates. We can write down the corresponding function as a wave function as a radial part multiplied with a spherical harmony. Okay. So it turns out that, well, let's just draw this as XYZ frame, and let me try to draw these spherical coordinates. So for a point, the radial coordinate is the distance to the origin. Theta is the angle with the z-axis, and then phi is the angle on the xy plane. So under inversion, that point is going to be transformed into that point. in which case this angle becomes pi minus theta, 180-degree minus theta, and phi becomes, yeah, let's see it like this, r theta phi. Under inversion, they are going to be transformed into r pi minus theta phi plus pi. Okay. Phi angle increases by 180 degrees, theta is somehow switched, and that's the transformation. Okay. So as a result, to actually understand how this thing transforms under parity, we have to look at the spherical harmonic part. So therefore, the parity eigenvalue should depend only on these two quantum numbers and not on the principal quantum number. Okay. So it turns out that the state psi NLM is basically transformed into -1 to L psi NLM, right? So the parity is equal to -1 to L. Okay. So the L values are 0, 1, 2, 3, and so on. We actually use the letters S, P, D, F, and so on for these orbitals. So for S orbitals, the parity is positive. For P orbitals, it's negative. It is positive for D, and so on. Right? It just goes alternating. Okay. If we just look at this, I don't know, the levels in here. So we have the 1s level, and we have 2s and 2p levels. So that's 2p. And then we have 3s, 3p, and 3d levels. 3s, 3p, 3d levels. So all the s levels have positive parity. All the p levels have negative parity. All the d levels have positive parity. Okay. In a transition, the parity must be conserved, right? There are these selection rules that I need to write down in here. Selection rules for transitions involving, let's say, emission or absorption. It doesn't matter which one. Of one photon. Okay. So basically the rule says that delta L should be equal to ±1, and delta M should be equal to ±1 or 0, right? So there is no delta L equal to 0 rule. So L value should change. So therefore, there cannot be a transition from, for example, P to P. That's not possible because it has to change. So therefore, there can be a transition between P and S, right? Or I mean, from this level, let's talk about absorption. From 2p level, by an absorption, there can be a transition to the 3s level or a 3d level, but there's no transition in the other direction. So as a result, the transitions are like that, right? So from S to P or D to P and P to S, and from here, this P to S as well. Okay. So all of these transitions actually involve a change in the parity. So that means parity of the atom must change during, must change in the transition. Sorry, not during, but in the transition. So how can we justify this with the conservation of parity? Well, basically we have to claim that the photon should actually have negative parity. It should have an intrinsic negative parity. So I'm going to think about this like that. So that's the 2p to 1s transition. Okay. Transition. You can think of this like the hydrogen in the 2p orbital. So I'm going to write this in like a chemical reaction kind of thing. In this transition, a single photon is emitted, and the hydrogen atom is transformed into this. So in this case, the parity is -1 for the 2p state and +1 for the 1s state. So therefore, the wave function for the photon should have negative parity. All right. I usually, I can actually express it like that. So the wave function before the transition is basically the wave function of the atom in the 1s state, right? Let's just write this thing down. So that's the, I don't know, the position of the electron, let's say, right? But the wave function after the transition is, sorry about that, so that's actually 2p. So the wave function after the transition is the wave function of the electron multiplied with the wave function of the photon. In that case, I mean, I'm just writing this symbolically. So the wave function of the photon should depend on the position of the photon, right? So that's the simplest possible picture. So when I talk about the inversion operation applied on psi before, let's say, t before, so that's essentially this inversion operation applied on the 2p state. And in this case, I know that the parity, well, parity of the 2p state is -1. So therefore, in the initial state, therefore, the parity is equal to -1, expectation value of the parity, right? Because it's a parity eigenstate. Okay? So because of the conservation of the parity of the state after should also be equal to -1. This implies that, right? So let me just write down the arrows like this. So the parity of the state after the transition should be equal to -1. Okay, but in that case, if you just look at this expression, so we have the parity applied on the wave function of the electron, that's 1s, and the wave function of the photon, right? So both of them should be inverted. So it turns out that, right, the 1s state does not change sign under inversion, but somehow the photon's wave function should change sign. Okay, so let's say it like this. Therefore, the photon has an intrinsic Hawk parity. And so this parity selection rule somehow enters into the selection rules, actually. Okay. So there is a related discussion in here from the transitions from the level 2s. So in this transition, in this 2s to 1s transition, well, both the initial and the final states have even parity. And so as a result, it's not possible that a photon is emitted because a photon has odd parity, right? So the parity would be violated in here if this transition involves two photons, right? So it's basically is against this selection rule in here. In any case, so what happens in here is that this transition actually takes place, but it actually involves the emission of two different photons. So we don't have a single photon emission in here, but two photons. Right? So let's just write this thing down like that. So from the 2s hydrogen atom, so that's the initial state, it just emits two photons, and the hydrogen atom is converted into the 1s state. So parity is conserved because the initial parity is +1, and both photons have -1 parity. If you just multiply all of them, so the final parity of this final situation is also even +1, and so therefore parity is conserved in this kind of a situation. Okay, so that's actually a well-known transition. Since it involves the emission of two photons, it's actually a very slow transition. So the lifetime of the 2s state is actually much longer than the lifetime of the 2p state. Okay, so that's basically the end of the parity discussion, right? So inversion symmetry has some implications. So weak interactions, of course, violate the inversion symmetry. And so the Wu experiment is a clear demonstration of this fact, but in weak interactions, we have other manifestations of violation of that symmetry. In the other cases, electromagnetism, for example, the inversion symmetry is there, right? And so therefore, we also see the signs of that symmetry in lots of different things. So the transitions, atomic transitions is one example. Since a single atom is always inversion symmetric geometrically, atoms have this symmetry too, and so therefore the energy levels somehow display that symmetry. So I can classify all the energy levels by their parities, and so we actually see the features of those transitions in this kind of situation. Okay, so I think I can only add the molecules in here. So there are some molecules like, I don't know, the water molecule, for example, it doesn't have any inversion symmetry. Either inversion kind of changes its shape, for example. I don't know. I can actually even talk about some molecules that doesn't have these kind of symmetries as well. In that case, right, I mean, the energy levels do not have this parity property, and in this case, I mean, you also see the signatures of these in the transitions as well, right? So that's something that molecular physicists actually know. There's one final thing. So I just made a very short introduction to representations. So basically, the idea is this: G is a group. I have actually done this earlier. G is actually any group. It can be a finite or an infinite group. I don't actually say anything in here. A is a function from the group to, let's say, n by n matrices. See? Such that, well, it satisfies that property. The product of AG and AH is going to give you the A of GH, right? So in any case, so for every group element, we associate a matrix to that group element in such a way that the matrix product, if group elements are represented by these matrices, then the product of two group elements is represented by the product of the corresponding matrices or something like that. Okay. So basically, you can do the matrices obey the same multiplication table as the group elements, right? In any case, so then A is called, it's actually called n-dimensional matrix representation, or just representation of the group G. Okay. So we just define this like that. A is simply a homomorphism. A is a homomorphism, actually. Homomorphism. So we have this restriction that these matrices are invertible matrices, so that's important. A is a homomorphism because A is essentially a transformation from the group into the general linear group of n by n complex matrices, actually. So in general, we are going to talk about complex matrices. Even for real physical problems, these kind of representations are going to be used all the time. So as a result, this is important. So in any case, since A is a function from one group to the other one satisfying that property, it's actually a homomorphism, right? So therefore, it satisfies these properties. So identity is actually represented by the identity matrix, which is simply the diagonal matrix where all diagonal entries are equal to 1 and all off diagonal entries are equal to 0. Right, let's just show it like that, all right? So that's 0. And the second thing is the inverse of a matrix has a representation which is given by the inverse of the representation. Okay. I actually express it like this. If an abstract group element is represented by a matrix M, then the inverse of that group element is represented by the inverse of that matrix, right? That's essentially what it means. So that the product of these two matrices also gives us the identity. Okay, so these are the two basic properties. Next week, I'm going to talk about more complicated properties of matrix representations. Basic idea is that these matrix representations are actually they are going to appear in the physical discussions of the symmetry. They are going to tell us how the wave functions, for example, transform under symmetry operations. And we would like to be able to express these representations in terms of some simpler, more fundamental, smaller representations, actually. That's what we are going to do. Okay, so this part of the course is going to be a little bit more mathematical from that point on. Okay, have a nice day. Let's finish this.